Hello everyone, let's look into different components or different groups of the intrinsic leakage power, and each group has got its own syntax. Okay, so to start with, we have got the leakage underscore current group. This itself is a syntax of this particular group. So leakage underscore current is the one that we were talking about. It's basically nothing but the static current that we have been talking about in the last video, and the way to represent the leakage current is something like this. So we'll take an example of this particular flop. So remember, this is the flop that we were using for our timing characterization. It has got the power supply, it has got the ground connection, and it has got the inputs that are toggling at different rates. So we'll consider one of the example of one of the rates of at which the D is toggling, at which the clock is toggling, and try to create or try to generate the power numbers or the leakage numbers for this particular flip-flop. Okay, so anything which is so there are two components of current over here. One component is the current which is entering into the cell, and there is another current, another component of the current that exits out of the cell. So these two components needs to be modeled under the leakage underscore current group, and there is one more thing that needs to be taken care of. Any current that is entering into the cell and the current that is going out of the cell, both should be same. Their polarities will be different, but the directions might be different, but the value should be almost same. If they are not, there is some additional component that needs to be modeled for, and we'll talk about that when we reach there. So to start with, let's try to look into the leakage current for this particular section. If you remember, this particular waveform it is very similar to what we did for our timing characterization. So we toggle our input, we'll toggle our input waveform, which is the D input. We toggle our clock waveform, which is the blue color, input, and this is your output. So there are multiple possibilities over here. One of the possibilities is whenever your clock and D both are equal to 0. Another possibility whenever your clock and D both are equal to 1. So these are the possibilities where you can see some amount of leakage current. So there are different possibilities. One of the possibility is whenever there could be a scenario where your clock is 0 and your D is high. So for example, if you look into this particular area, your clock is 0, your D is high, your D is 1, clock is equal to 0, and there could be another scenario where your input is falling and the output, where your D input is falling and the clock is also falling. So there could be four different kinds of scenarios. So if you have two inputs, D and the clock, there would be 2 raised to n, which is 4 different scenarios. So let's look into one of these scenarios and try to compute the leakage current for that particular scenario. So if you look into this particular scenario where your D is also equal to 1 and clock is also equal to 1, in this kind of scenario, if you try to plot the current waveform for a static logic level, which is logic 1, at this point of time, the leakage current waveform will look something like this. Okay, if you zoom into and this is the reason you see all these spikes is because it is in the range of nanoamps. So that's why it's very little, but you still see these spikes. And if you try to note the values of this particular current, it is almost the same. So for example, the top spike which is over here, it's something about 209 nanoamps, and the bottom one is about negative 210 nanoamps. So these are the leakage current values that we need to model for. Now there are two different values that we find over here. One is the positive value and one is a negative value, and these two values needs to be modeled in the leakage current group. So this is how we do it. So for example, leakage underscore current is a CCS power format. The format that you see over here, it's in a CCS format, and the way to write it is, if we write the cell is basically, let's say, my underscore D flip flop, which the one which we are modeling for. And if you see in this area, will all your timing related and the noise related information will come in this area. Then you have the leakage underscore current group, and you have this particular syntax, and it's again a state dependent current. So whatever current if you see, and if there is a condition called as when, it says that when your D and clock both are high. So the current that you see over here, those are all state dependent, and if there is no state available, the value of the when will be equal to default. So whenever the conditions, there will be multiple conditions. For example, we just now talked about 2 different conditions or 4 different conditions for if you have 2 different inputs. If you have D and the clock, you will have 2 raised to n, which is 4 different conditions available, and this is what I'm showing is for one of those conditions. If let's say if there is called as one, if there is when underscore default, and if there are if there is when underscore default, and if there is when equal to D and clock, and if suppose the scenario encounters a situation where it is not present in the when condition, it will take the default value, which is when equal to default, and whatever is being presented under the when equal to default, those will be the values that will be used as your leakage current value. Okay, so in this case, we are coming back to the situation that we were talking about. It is when is D and clock equal to high, and whenever your D and clock is high, the PG current VDD, the positive value of the current, will be 209 nanoamps. So it will be basically 209 nanoamps is the value that I have just put. This particular value will come from a timing library unit. So I'll talk about timing library units, where do we specify them and so on. So we'll talk about that when we reach into the next section, but this is the way you to specify it. So PG current of the VDD will be 209 amps, and PG current VSS, which is going to the ground, is negative 210 nanoamps. So if you closely observe over here, if you add this one and this one, this comes to about 0, or let's say it comes to about negative 1 nanoamps. Okay, so it is always possible. So ideally the value, the value that you see over here and the value that you see over here, if you add all of them, it should give you a value, or called if it should give you a value of 0 nanoamps. But in this case, let's say there is some additional 1 nanoamps that is being missing, so that 1 nanoamps comes from a different source, and we'll talk about that when we reach into the gate leakage current section. So we'll keep that for a hold. But typically the value which is present over here under the PG current VDD and the PG current VSS, if you add all of them, the value should be coming to be 0. Okay, because it should satisfy the Kirchhoff's law. And this was about the leakage current. Let's look into the second type of the intrinsic leakage power format, which is your leakage power. So it is nothing but similar to the leakage current, only that now we are representing the current in form of the power, and it is called as it's in the non-linear power format. So if you look into the formula for calculating the leakage power, it's nothing but it's very simple. It's basically you multiply the current with the voltage. So coming back to our same situation where your D was equal to 1 and clock is also equal to 1, you do the same thing. You calculate the leakage current, which was 209 nanoamps and negative 210 nanoamps, and with those particular values, you just calculate the P static or the static power as I static, which was in one case it was 210, and in another case it was 209 nanoamps. So you take those values, you keep it over here, you multiply it by VDD, which was 1.8 volts in our case. So that's the basic formula to calculate the static power. So in this case, if you look into the static power value, it is, let's say, 210 nanoamps into 1.8, which comes to about 378 nanowatts or 0.378 microwatts. So depending upon the library conditions, or depending upon the timing library unit depending on the library unit for the leakage power, these particular values are being specified. So if the library unit specifies its nanowatts, so we just put the value of 378. If the library unit specifies the value of microwatts, we put 0.378. I'll show you where do we specify the leakage power unit. So first of all, the way to specify the leakage power group is something like this. It's again a state dependent thing. So leakage power when is equal to D and clock. So it says that whenever a D is high and clock is high, you get a value of 0.378, and the units of this one will be defined by a certain table. So basically we have a table, or we have a section in the library that specifies all your timing library, all your leakage power and different kinds of units, and this is that particular section. So when you open up the library, in the initial section, you will see all these different units which is mentioned over here. Under that, you will see a leakage underscore power underscore unit, which is 1 microwatt. It could be 1 microwatt, it could be 1 nanowatt. So if it is 1 nanowatt, you need to specify the value of 378 in the powers in the unit section, in the value section over here. But if it is 1 microwatt, you just need to specify 0.378 over here. Okay, so that was about the leakage power group. There is third group, which is the cell leakage power group. So what we'll do is that we'll stop at this point and we'll start with the cell underscore leakage power group, and the other group, which is the tunneling current, that was coming under the gate leakage current group. So let's try to cover both of them in the next video. Thank you.